Any questions before we move on? Okay, so we left off on Friday. We were talking about fin performance. So we are looking at a couple different metrics for fin performance, and the first one that we talked about was fin effectiveness. And note that this, I guess I can write it on here, this metric is just for a single fin. In a little while we'll talk about efficiency for an array of fins. So the effectiveness is defined as the heat transfer rate with the fin divided by the heat transfer rate that would be occurring if the fin was not there. So the surface area that we use for this comparison is the surface area at the base of the fin, so the cross-sectional area at the base of the fin. So basically how much area the fin is occupying. So then we said that, so Friday we kind of derived all of those cases for the temperature distribution for all the different boundary conditions, and we said that we could find the effectiveness for each of those different fins by dividing the previous expressions that we came up with for the heat transfer rate for those different boundary conditions by this quantity HA sub C comma B theta sub B. So just the heat transfer rate that would be occurring without the fins. And then we said, okay, let's just do that for this one very simple case of an infinitely long fin. So the effectiveness for an infinitely long fin is this quantity here. And we assumed that the convection coefficient is going to be the same with and without fins, which is a common assumption. Okay, so now we're going to talk about what that kind of infinitely long fin effectiveness, how we can look at it. So let's just rewrite that here. How we can look at it and what it can tell us about when it's good to use fins. Okay, so looking at this equation, we can see that the fin effectiveness is going to increase when K is higher. So fins are more effective if you use a material that has a high K. And you should have seen this in your lab where the fins that were made of materials with higher thermal conductivities had higher temperatures at the tip of the fin. Okay, so high K, and then also if this ratio of perimeter to cross-sectional area is high. So if you think about what kind of geometry would give us a high ratio of perimeter to cross-sectional area, that's a very thin geometry. So you have like kind of a long, very long width with a very small cross-section. So that's often why thin fins are used. So we'll say high P divided by A sub C ratio, i.e. thin fins. And the last thing it tells us is that the effectiveness is typically higher if the convection coefficient is smaller. So you have a smaller quantity on the bottom that's going to give you a higher ratio. So basically that's saying that it's easier to justify the use of fins if your convection coefficient is small. So for example, if the fluid, the ambient fluid, is a gas, or if you're talking about free convection, which was the case, both of those things were true for the lab. So just free convection in air is typically significantly aided by the use of fins. Okay, so if H is small, for example, free convection in a gas. Okay, so that's it for effectiveness. We're going to talk about fin efficiency now, which is a different thing. Any questions about effectiveness? Okay, and again, for now we're talking about the efficiency of a single fin. So here we have the efficiency is defined as the ratio of the actual fin heat transfer rate to the maximum possible fin heat transfer rate. So previously with effectiveness we had the heat transfer rate divided by what the heat transfer rate would be if there were no fin, and this is the actual rate divided by the maximum possible. So the fin heat transfer rate divided by maximum possible. Maximum possible fin heat transfer rate. Okay. So writing this out, that would be A to sub F is equal to the actual fan heat transfer rate that we're seeing divided by Q sub max. And if you remember, we talked about the maximum possible heat transfer rate that it could occur from a fin is when the temperature along the entire fin is equal to the temperature at the base. So that's when you have that kind of infinite K condition. So that's going to be equal to the actual heat transfer rate divided by the heat transfer rate by convection if the temperature of the entire fin was equal to the temperature at the base. So this is just saying A sub F, so the surface area of the fin, and then theta sub B, which is, remember, our theta is our excess temperature. So that is theta sub B is the temperature at the base minus T infinity. So this is basically saying that the temperature along the entire fin is equal to the temperature at the base, and we're just defining it in terms of this theta here. Okay, and so then we'll say A sub F is the surface area of the fin. And then, as before, we wrote this out last time for the effectiveness. We can say the efficiency for straight fins of uniform cross-section, we can find that, just like with the effectiveness, by dividing the previous expressions that we had for the fin heat transfer rate for the 4 different boundary conditions, cases A through D, by this quantity, H A sub F theta sub B. So the efficiency for straight fins, uniform cross-section, so we won't write out explicitly the equation for each of them, but you have all of the expressions for the 4 different cases. So can be derived by dividing previous expressions for Q sub F which we showed in cases A through D, by this quantity H, A sub F, theta sub B. Okay. Questions on that?
So with those, we were using A sub C, which is the area of the cross-section. That's area of the cross-section of the fin, yes?
So for effectiveness, you mean?
Back with the A through D equations. Right, QF. So in case B, when there's negligible heat loss from the tip,
Yeah.
QF is square root of HP K A sub C.
Yes, just the cross-sectional
Just
area of the
cross-section
fin.
of the fin.
Yeah. Yeah, there's like 10 different A sub whatevers. And I did try to write out what all of them are in the nomenclature sheet that's on Canvas, but yeah, it's could keep it straight. Okay. So we'll move on now to overall surface efficiency. So this is for an array of fins. And that is defined as eta sub naught. Or denoted by eta sub naught. So as before, we're dividing the actual heat transfer rate by the maximum possible heat transfer rate. So for this case, because we're considering a fin array, the surface area that we're going to be talking about is the total surface area of the fins and the exposed portion of the base. So it's the ratio of the actual heat transfer rate from the total surface area of the fins and the exposed portion of the base to the heat transfer rate, the maximum heat transfer rate possible, which would be if that same entire surface area was at T sub B, the temperature at the base. So if the base and all of the fins were at T sub B. Okay, so let's write that down. So that is the actual heat transfer rate from the total surface area, A sub T, divided by the heat transfer rate if the total surface area was at T sub B. So the equation for that is eta sub naught is equal to the total heat transfer rate divided by this QT max, so the maximum possible total heat transfer rate. That's QT divided by H A sub T theta B. So here we just have, instead of the cross-sectional area, or the surface area of one fin, we have the entire surface area of the entire fin array. And we'll write down an expression for this A sub T. So that's equal to the number of fins times the surface area of each fin, which was the A sub F that we were looking at before for the single fin efficiency. So the surface area of one fin, plus A sub B. And here we'll say this is the exposed area of the base. Exposed surface area of the base. Okay. So we want to come up with an expression for Q sub T as well, because it's just this kind of like lump heat transfer rate from the fins and the base. So that's going to be first the heat transfer rate from the fins, so the number of fins, times the fin efficiency, the single fin efficiency, times the maximum possible heat transfer rate from that fin. So if you remember, this is just drawing on this equation for the single fin efficiency, which I'll pull back up here. So Q sub F from a single fin is just equal to the fin efficiency times H A sub F theta B. And then if we multiply that by the number of fins, then we get the heat transfer rate from all of the fins. Okay, so that's the heat transfer rate from all of the fins, and then we have to add in the heat transfer rate from the base. So the convection coefficient times the exposed area of the base times theta sub B. So remember, the temperature of the base is going to always be T sub B. That's how it's defined. And then we have this efficiency term in here for the fins because in actuality, the temperature of the fins is not always equal to the temperature at the base. So that's where that term comes in. Okay. And again, this is assuming that H is the same between the finned and non-finned surfaces. So we can rearrange this to get an expression for the overall surface efficiency in terms of the individual fin efficiency. So that's 1 minus N times AF over A sub T times 1 minus eta sub F. So now if you just know the surface area of a single fin, the total surface area of the array, and the efficiency of a single array, or of a single fin, plus the number of fins, you can calculate the efficiency of the overall array without knowing any of the heat transfer rates in particular. Okay, any questions? Okay. I think it might be helpful, I didn't draw this initially, but it might be helpful just to put up a little picture of the fin array so you can kind of see where all the different areas are or how they're defined. So let's just take a look, like a side view look. Have 3 fins, 3 straight fins. So the temperature at the base is going to be the same for all of the fins. So it's basically this temperature right along this surface at the base of the fins. Each fin is going to have a surface area, A sub F, and remember that doesn't include the tip because that's accounted for based on which boundary condition you choose. Because you don't necessarily have convection from the tip of the fin. And then A sub B is the area of the base. So basically all of these different areas kind of added up. And then the total surface area, you can look here at the drawing. So now we have NAF plus A sub B, where N is the number of fins. Hopefully that makes a little more sense having it drawn out. Okay, we're going to switch topics. So any last questions on fin performance? Okay. So just like before with convection, where we kind of needed to learn a little bit of the basics of convection in order to apply it at boundaries and kind of be able to work with simple convection problems, it is now time to introduce radiation. So again, we're going to just introduce radiation, the concepts, and some of the kind of simple equations to work with radiation that is, heat loss from surfaces. And then in later chapters, we'll dig more into calculating like the specific parameters that go along with radiation rather than just being given them like you will be for now. And this is going to be especially important for the upcoming lab next week, where you're going to have an object that is losing heat by free convection, natural convection, and radiation. And you can't really neglect the radiation. Okay. So, introduction to radiation. Okay, so we talked about this a little bit at the beginning of the quarter, but if you remember, thermal radiation is energy emitted by any matter that's at a non-zero temperature, and it's transferred by electromagnetic waves. So instead of having like molecules that are moving around and bumping into each other and transferring heat, you have, it's caused by like changes in the electron configurations of the structure. And if you have electrons that end up in a lower energy level, it's going to emit electromagnetic waves. And then if an object absorbs electromagnetic waves, you're going to end up with electrons in higher energy configurations. So kind of the cool thing about radiation is it doesn't need a medium in order to transmit heat. So you don't need a gas or a liquid or a solid to be there to kind of transfer the heat via molecular vibrations. And it actually works most efficiently in a vacuum. So let's write some of these things down. Okay. So energy emitted by any matter at a non-zero temperature. So that's pretty much everything. And this is non-zero absolute temperature. So if it's above 0 degrees Kelvin. And that is solid, liquid, or gas, although we'll primarily talk about radiation from solid objects. So heat is transferred transferred via electromagnetic waves and it can occur independently of convection and conduction or in tandem with. So they can all three occur simultaneously. So it can occur independently of or in tandem with conduction and convection. And in real systems, you'll often have all three modes of heat transfer occurring simultaneously. And then it's related to changes in the electron configurations. Does not require an intervening medium. And is most efficient in a vacuum. So we'll draw a little surface that's at finite temperature, and we'll refer back to this as we're developing some more radiation concepts. So for now, we're going to say it's at this given temperature, T sub s, and that you have, say, some gas up here that is at some temperature and has some convection coefficient H. So we'll talk about convection occurring at the same time as radiation. So this surface, because it's at a finite temperature, is going to emit radiation at a given rate of watts per meter squared. And how many watts per meter squared it emits is called its emissive power, capital E. So we'll say E is emissive power. In watts per meter squared. And to talk about how efficiently something emits radiation, we often refer to this concept known as a black body. So a black body is basically an ideal emitter of radiation and absorber, which we'll talk about in a minute. And it emits the most radiation possible per unit area for a surface. So we'll say a black body is an ideal radiator. And the emissive power of a black body, E sub B, is equal to sigma T sub s to the fourth. So here, T sub s is the surface temperature and note, this is important, this is not a delta, so this is in Kelvin. And this constant, sigma, is called the Stefan-Boltzmann constant. And it is equal to 5.67 times 10 to the negative 8, which is convenient for remembering it.
Yes.
Watts per meter squared K to the 4th. Okay, so we will talk about the emissive power of a real object or a real surface, kind of relative to the emissive power of a black body. So the emissive power of a real surface slash object. Typically talk about radiation from a surface, but it's from the entire object itself. Is E equals epsilon E sub B, which equals epsilon sigma T sub S to the 4th. So we've basically just taken the emissive power of a black body and then stuck this factor epsilon in front of it to account for how well a real surface actually emits radiation. So this epsilon is the emissivity, and it can take on values between 0 and 1. So basically, if it's 0, the surface emits no radiation. If it's 1, it's a perfect black body. And anywhere in between there, it's a better or worse emitter of radiation. And the emissivity depends on the surface material and the surface finish. And in the lab next week, you're going to be testing different objects with different platings or coatings. So you can see how basically the surface finish of the objects, which are otherwise similar, changes the radiation. Okay, so now we will talk about irradiation, which is similar, but now instead of talking about emitting radiation, we're talking about radiation that's incident upon a surface. And we can add that to our little sketch here. And irradiation is denoted by a capital G. So radiation being received by a surface. So this emission and reception both happen simultaneously. Okay, so capital G. And if it's absorbed, it increases the thermal energy of the object. And that happens because you end up with electrons in higher electron configurations. So typically, unless you're dealing with a black body, only a fraction of the radiation that is incident upon a surface is actually absorbed. So only a fraction of the irradiation is absorbed. So we'll say G absolute is equal to alpha times G. So radiation that isn't absorbed is either reflected or transmitted through the object, and that radiation does not affect the thermal energy of the object. So what we actually care about is how much of the energy is actually absorbed by the object. So here, this is let's see. Absorbed radiation, absorbed irradiation, this is the total irradiation. And then alpha, similar to epsilon, is a property known as the absorptivity. And as with emissivity, it can take on values between 0 and 1. So if it's 0, none of the radiation is absorbed. It's basically either all transmitted or reflected. And if it's 1, it's a perfect absorber, so a black body. So it's absorbing all the radiation that's incident upon it. And we'll say, just like with emissivity, this is a property of the surface. So we can have a couple of different cases. So if we have alpha less than 1 with an opaque surface, now we have some of the radiation being absorbed, and because the surface is opaque, some of it's going to be reflected. If we have alpha less than 1 and we have a semi-transparent surface, some irradiation is reflected and or transmitted. So a semi-transparent surface, some of it can be reflected and some of it can be transmitted through the surface. And like I said before, reflected and transmitted energy does not affect the thermal energy of the surface. So we'll say reflected and transmitted radiation does not affect thermal energy of the object. It has to be absorbed in order to raise the energy of the object. So we'll introduce our rate equation. There's a decent number of kind of assumptions that go along with this equation, and we will talk about them in more detail when we get to the radiation chapters. But for now, we'll just assume that the assumptions that are baked into this equation hold true for the cases that we're considering. So if you have radiation exchange between a small surface and a much larger isothermal surroundings, yes.
Do we not care about transparent surfaces?
Fully transparent surfaces?
Yeah.
Yeah, you would have basically like full transmission through the surface, but a perfectly transparent surface that,
Black box.
yeah, it's very,
Cool.
yeah, I would say rarely would occur. Yeah. But typically, good question. So typically, we consider liquids to be opaque and then gases to be transparent. So essentially, you don't have much radiation being absorbed by gases. Typically, you would have like radiation from an object, and then it would be absorbed by like the wall behind it or something. And then solids can be opaque or semi-transparent. But we are concerned mostly with solids in our discussion of radiation. So opaque or semi-transparent. Okay, so radiation exchange. These are kind of weird restrictions, but we'll see why this is the case later on. Radiation exchange between a small surface and large isothermal surroundings. So surroundings that are all at the same temperature. Large isothermal surroundings. The radiation heat flux, which is equal to the heat transfer rate divided by the area, like always, is equal to the emissivity times the Stefan-Boltzmann constant times T sub s to the fourth minus the temperature of the surroundings to the fourth. So this is the temperature of the surface, and this is the temperature of the surroundings. Okay. And that's the equation that we're primarily going to be working with. It's useful to express this in kind of a format that we've seen before. So write it similar to the convection rate equation, where we have this radiation heat transfer coefficient H times the area times the surface temperature minus the surrounding temperature. And by comparing these two equations, we can show that H sub r must be defined as epsilon times sigma times the temperature of the surface plus the temperature of surroundings times the temperature of the surface squared plus the temperature of the surroundings squared. And so that's just choosing to write this equation in a form that looks like the convection rate equation and saying, okay, if we do that, then to make the math work out, this is what this H sub r has to be equal to. So here we're saying that, so radiation is dependent on the temperatures to the fourth power. And here we're writing it as proportional to the difference between just the temperatures raised to the first power. But unlike the convection heat transfer coefficient, which doesn't depend on the temperatures very much, this H sub r does. So it's just a different way of looking at it, but you've still got all the same kind of dependence of this original equation in there. So the reason that we look at it this way is because we often will have combined convection and radiation from a surface. So it's convenient to lump the two together by writing the radiation equation to match the convection equation. Sorry, combined convection and radiation. So when that occurs, we have this total Q, which is going to be the Q due to convection plus the Q due to radiation. And so that'll equal our convection rate equation, HA times T surface minus T infinity, plus our radiation rate equation, H sub R times A times T surface minus T surroundings. So now just writing this as a combined heat transfer rate from convection and radiation using all equations that we're familiar with. And if we want to rewrite it in terms of our alternate radiation equation, we can. So this is just to show that these two are equivalent. But if you have a situation where the ambient temperature of the fluid is equal to the temperature of the surroundings, which will often be the case for natural convection. You just have an object sitting in a room and the air around it is just the ambient temperature, which is the same as the temperature of the surroundings. Then you can write this as the total Q is convection plus radiation, which is equal to this effective H times area times Ts minus T infinity. So here we've just said, okay, the temperature of the surroundings is equal to T infinity. We're going to factor out this A T sub S minus T infinity, and then we're just left with this H plus H sub R. So it's just this kind of lump parameter that includes the combined effects of convection and radiation. So, final note, just like with our other forms of heat transfer, we can write down an equation for the thermal resistance of radiation. So the thermal resistance of radiation.
Can you move it up?
Yep. Thank you. So if we look at our rate equation, T surface minus T surroundings, and just rewrite it to have this 1 over H sub R A in the denominator. Then just like before, our thermal resistance of radiation is going to be equal to 1 over H sub Ra. And kind of an interesting note, and I may work a problem like this tomorrow in recitation. If you have surface convection and radiation occurring at the same time, then they're going to be, they're going to look like resistances that act in parallel. So that's actually another kind of neat application of the thermal resistance concept, which we didn't talk about parallel resistances before. But it's interesting because if you have them acting at the same time, right, it's not the heat going through one then the other. They're acting together. So the convection and radiation act in parallel. So we may see a problem with that tomorrow. Okay, and then recitation tomorrow, do some practice problems on fins. And Wednesday, we'll start with transient conduction.